Welcome to Lecture 2 on polynomials. Alright, in the last lecture we talked about functions, so let's start by reviewing some things about functions. First of all, not every curve is a function. In order to be a function, a curve has to satisfy the vertical line test, which means no matter where we draw a vertical line, it can intersect the curve at only one point. So, functions must satisfy a vertical line test. We also introduced two different types of variables. You have your variable on your x-axis and your variable on the y-axis. The variable on the horizontal x-axis is known as the independent variable. It is the question that you are asking, the function. The answer that you get out that depends on the question is called the dependent variable. The range of possible questions that you can ask is known as the domain of the function. So it is the smallest value on the horizontal axis to the largest value on the horizontal axis. So in this case, our domain is -4 to 4. And remember that we used square brackets when those points are included in the range. The domain, and then the range of a function is the set of all possible answers that we can get out. Now, it's not from the edges of the domain, it is the most extreme points, so that goes from everything from there to there. So this includes things from approximately 4.6 all the way up until 5.6. All right, and I'm going to use open brackets just because they're approximate, and I don't know if those points are exactly included. So the x has a domain, and the y has a range. Our dependent variable is is y, and our independent variable, the question, is x. All right, so that is an introduction to functions. Today and in the next few lectures, we're going to be talking about several functions that are of particular relevance in biology that come up in biological situations, and one of those is a polynomial. So if you have ever heard of a regression, which is a method for fitting data, those regressions occur with polynomials. Polynomials are very flexible and hence they're very useful. In general, a polynomial can be written in the following form, where we have some dependent variable f of x that depends on the independent variable x in this case. But notably, we have constants a0, then a1x, a2x squared, and so forth. All right, up to some term an x to the n. Some examples of polynomials include y equals f of x, 3x squared, or 3 plus 7x squared. So know that some of the constants can be 0. In this case, a1 is 0. So if we wanted to write this out in full form, we'd have 0 times x plus 7x squared. So just because you have an x term in here does not mean it has to show up in the polynomial, because the constant can be 0. All right. Similarly, the constants can be negative. So the constant is everything, including the plus or minus sign. So here we have 0. So once again, a 0 constant plus a positive 3x plus a minus 17.2x cubed. And there's actually a plus 0x squared in there as well. So that minus is included in the constant, and this is important when, for example, evaluating the quadratic equation to find the roots of a quadratic, which is a special polynomial. All right. Finally, the terms don't necessarily have to be written in order, so keep track of the order that they're in. So if we were to rewrite this in order, we would have 3 plus 14 z plus 2z squared. So note that you should always look for the term that has the highest order or the highest exponent on the independent variable in order to figure out what kind of polynomial it is. Now, I've mentioned this highest term, so here we have a squared term, here we have a cubed term, and here we have a squared term, and we call that term the degree of the polynomial. So the degree of the polynomial is the largest value of n such that the constant an is greater than 0. So in this previous example, we could add an additional term to this here, which is 0z cubed, and that term would not show up, and all other terms after this, so 0z to the fourth, would all have constants that are 0. So the largest one of the constants that is not 0, for example, in our case, the 2 in this function determines the degree of the polynomial. So the degree of this polynomial would be a squared. It's the n. It's the exponent. All right. So for some examples here, what degree does this polynomial have? Once again, we look for that largest term. In this case, it is the squared term, so this has degree 2. In this term, it is a 3, so it has degree 3. And in this case, it is once again a 2. Note that, yes, once again, the functions do not, or the terms do not have to be written in order, and so you want to look for that largest term. All right, so some of these lower degree polynomials have are so common that they actually have special names to them. First of all, if we have a degree 0 polynomial, that means that even we can have like a 3, but even the x term has a leading constant of 0, then this simplifies to just being 3, and this is known as a constant. So that is the definition of a constant. A line is a polynomial of degree 1, so we have 3 plus 2x, for example, but then we have 0x squared term. A quadratic, which you are probably tired of hearing about, has an x squared term. It doesn't necessarily have to have any of the other terms, but it has to have an x squared term in it. A cubic is a x to the third, a quartic is an x to the fourth, and a quintic is x to the fifth. All right, so some of these lower order polynomials are not only so common that they have names, but they're so common that you should be able to recognize their shapes. So for example, we have constants here. What degree are these polynomials? They are degree 0. So we have two different constants here. We have the red constant and the blue constant. We could also have a line. This is a degree 1. We could have a quadratic. So start by looking at how many humps that they have. If they're completely flat, they're constant. If they have a slope, they're a line. If they have one hump, they're a quadratic. This is a degree 2. And finally, we have a cubic, which has 2 humps. They're a little bit hard to see here, but you have 1 hump, 2 humps. So a hump here and a hump here. All right, so there's even more that we can tell about these quadratics, but in order to do that, we have to think about these other terms that we've talked about functions. For example, the y-intercept. So the y-intercept of a function is the point where it intersects with the vertical y-axis. So if I were to draw that in this function, or in these cases, it would be this point here and this point here. How do we find the y-intercept? By definition, the y-intercept is the point where we replace x by 0. So when we plug in x equals 0, then we end up, by definition, with the y-intercept. In the case of a polynomial, this is particularly simple. So if we plug in x equals 0 into every single term of the polynomial, then each one of these x's is going to drop out except for the a0 term, which is not multiplied by any x's and hence does not necessarily equal 0. So in the case of this function here, we have f of x is equal minus 2.4 plus 1.4 x. If we plug in x equals 0 for our y-intercept, that simply becomes minus 2.4. Make sure that when you calculate a y-intercept that you check it off of the graph that you have. And so if we look here, yes, that looks about like minus 2.4, so we're good. Okay, similarly, if we plug in f of 0 for this quadratic here, note that it has one hump, then we end up with a value of 2.4, positive 2.4. And yes, if we check off of our graph, yes, it's about 2.4. All right, so we can use those y-intercepts to tell us a lot about these polynomials that we had on the previous page. So for example, we know that a0 is greater than 0 here because the y-intercept is greater than 0. Okay, similarly, the y-intercept here is less than 0. And I've done a similar thing for all of these other plots where the blue function, oops, that's not quite true, but you have a0 less than 0, a0 less than 0, and the y-intercept is greater than 0. Here we actually have the opposite situation where a0 is less than 0 in this case, and a0 is greater than 0 in that case. All right, that's not the only thing we can learn. We also know that if we have a quadratic, okay, so if we consider the point, the y-intercept where we plug in 0, then we have f of 0 is equal to a0, okay? So that is this point here. This next term, a1x, defines a line at that y-intercept. So the next term defines this line right there and this line right here. So in the blue case, that line has a negative slope, so therefore we know that a1 is less than 0, and in this case, a1 is greater than 0. So the line at the y-intercept defines the value of a1. So similarly here we have a line at that y-intercept, so we have that a1 is it greater than 0 or less than 0? Here the slope is increasing, so we have a1 is greater than 0, and here we have that a1 is less than 0. So if you don't know if the slope is increasing or decreasing, think about a car or a bicycle riding on that line. If the bicycle is going uphill, then that is a positive slope. If the bicycle is going downhill, that is a negative slope. Similarly, we can have a little trick to figure out what a2 is in the case of a quadratic. If we see a sad face, a frowny sad face, then a2 is negative. So a sad face means that a2 is less than 0. If we have a happy face, then a2 is greater than 0. All right, so you should be able to look at a polynomial of low degrees, specifically 0, 1, and 2, and tell me the values of a0, the magnitude of a0, a1, and a2, whether they are greater than 0 or less than 0. All right, so we talked about the y-intercept. Not only do we have a y-intercept, but we also have the roots of a polynomial. Remember that the roots are where that function intersects with the horizontal x-axis. So the y-intercept is where you intersect with the vertical axis. The roots are where you intersect with the horizontal axis. Unlike a y-intercept, there can be multiple roots because they would not violate the vertical line test by having multiple of them. All right, so in the case of a line, a degree 1 polynomial, we have at most 1 root. And in particular, we can find that root by asking when is this function f of x equal to 0. Doing a little bit of algebra, we have minus 2.4 equals 1.4x. Dividing through by 1.4, we have minus 2.4 divided by 1.4 equals x. And I have the value of that here. Which is equal to, I messed up. I should have a minus sign right here. So we divide by minus 1.4, and that gives us 1.74. All right, similarly, we can find the roots of this polynomial, the quadratic, the degree 2 polynomial, which has at most 2 roots. So it could have 1 root and 1 complex root, or it could have 2 complex roots, which you wouldn't see in the plot, but you have at most 2 real roots, which means that you can see the intersection between the horizontal axis and that curve in at most 2 places. So we have f of x here is equal to 2.4 plus 1.4x minus 0.8. x squared. And remember that when we talk about these negative constants, we have to include that negative sign in the constant. To find the roots of a quadratic, we use the quadratic equation. To do that, we use this as our constant a, this is our constant b, this is our constant c, and that negative sign is included in there. And then we have that x is equal to negative b plus or minus, so we have to have potentially 2 roots. So one of those roots goes to the plus, one of those roots goes to the minus, plus or minus the square root of b squared minus 4ac all over 2a. And I'll let you work this out at home, but you should get values like x is equal to minus 1.06 and x is equal to 2.84. So if we look at our plot, sure enough, one of them comes in just about halfway between the 2 and the 4. So that is going to be this guy here. And similarly, we have one that falls on the right-hand side of the minus 2. And so that is approximately minus 1.06. So we're doing okay. All right, so with that, I'm going to leave you with the self-study question for this lecture, and I'll see you in class.